People, are you ready? Because we're about to get deep. And when I say deep, I mean like a bad pun, hole through the dug all the, what if we were to dig a hole through the Earth? Dig a hole straight down through the center of the Earth and out the other side. You dig my graphic? Here's the hole. It's so dark. You go through here, through the center of the Earth. Here's the backs, on the back side of the Earth there, maybe down yonder in Australia. Uh, so yeah, we dig a hole right through the center of the Earth. You get it? It's deep, people. It's deep. What would happen to an object that was released in that hole? If you were to jump through. Now, this couldn't happen for a couple of reasons, right? The Earth is rotating, right? So maybe if we did it right along the Earth's rotational axis, that would help, because then then you wouldn't be moving tangentially relative to the Earth's axis. Okay. And what if let's also assume perhaps that the Earth is of constant density, which it sure isn't. Let's also assume that it's not wicked hot in the center. So, this is theoretical, of course, but it's fun to think about. So, we're going to talk about what would happen to this object that's hypothetically dropped into this hole. All right. And what would happen to the object depends on the forces acting on the object. And the forces acting on the object are only gravitational ones exerted by the Earth. So what we really have to know is, what does Earth's gravitational field look like inside this hole? All right. So here's the Earth. All right. And let's say you just dropped into the hole, and now this is a shell of mass that you are currently inside. You dig? Okay. And, well, let's take a hypothetical location right in the, am I recording? Yeah, okay. Let's take a hypothetical location right in the center, directly, perfectly in the center. You might be able to imagine that the gravitational field at that location is 0, and you're right. And why is that? That's the same thing as saying if you were to put a point mass, or any object, I guess, right at the dead center of this shell, what you would get are forces exerted by every part of this shell. And again, assuming a nice constant density of all this stuff, well, those forces from every individual infinitely small part are all equally sized and symmetrical, and thus, at that point right in the center, the gravitational field and or the gravitational force exerted on an object at that location are both 0. All right, but what if we were to take a different, a different location, like right here, off center? All right. Well, what I'm going to take are a couple of parts of the shell that, what's the word I'm looking for, that contribute to gravitational field at that location. Of course, there are other parts, right? There are there are corresponding parts on the back. See, get it? This is like in the front of the shell. That's like in the back of the shell, hence the dotted line. There are other parts. There's a part here in the front that corresponds to a little part here in the back, maybe, or something. I don't know. It's hard to. This graphic is tough to analyze, but you get what I'm saying. So let's just look at 2 of the corresponding parts and how their effects combine at this location. All right. Well, at that location, there are, let's talk about, for example, like this thing, let's call the mass of this thing M1, well, creates a gravitational field that looks like that, points toward that mass. And this second mass, M2 over here, creates a gravitational field, G2, that points towards it. And let's try to compare these G1s and G2s. All right, so G generally is G mass of field maker divided by distance from field maker squared. That's a general expression for how strong a gravitational field is. All right, so like G1 is 1, 1, 1, and G2 is G M2 R2 squared. Well, how much mass do each of these objects have? Well, that depends, right? We can say that these, well, let's see, G, over R1 squared. The mass of this M1 depends on how much area there is. There's an A1, and how dense this stuff is. And we can define an area density sigma that's mass per unit area. So we can say this is sigma A1. Yeah, it's okay, it's okay. Similarly, this is G sigma, oh boy, sigma. What I should have said, folks, is if you got a snack or a glass of water, you might want to get it because this is going to take a while. But it's pretty neat. Maybe play it at double speed. R2 squared. Okay, well, how big are these areas? Well, that depends. Dig this. There's something here that will pop up if I'm not, if I'm so, yeah. Here's these two cones, right? These two cones. You get it? Like, you do. You get it, right? You can see them. This one is this one, right? And so on and so forth. So, like these two cones, what's neat about them is, oh boy, well, they're similar cones, right? If we could take this one and slide it up here, you'd see it would fit right there, which says that if we look at some dimensions of these things, let's call, you know what, I'm going to change notation a bit. I'm going to take this, this distance, and instead of calling it R, I'm going to call it D. Here's a, well, this really is a D2. And this is a, no, that's a D1. This is a D1, and this is a D2. So this is D, yeah. So let's call this D and D and D. Sure, sure, sure. Now, these areas, right, this area here, we could say that this is G sigma over D1 squared pi R1 squared. I mean, Shanks just never stops calling. And this is G sigma over D2 squared pi R2 squared. And guess what? This similar, now this R, look, here's R1, here's R2. And guess what? Since these are similar cones, what we can really say is that D1 to R1 is the same as D2 to R2, or the inverse of that is actually more helpful for us because look, here we have R1 squared over D1 squared, R2 squared over D2 squared. And if we inverse these and square them, it's true that R1 squared to R2, well, sorry, to D, R1 squared to D1 squared is the same as R2 squared to D2 squared. And so these things are equal. Clearly the G and the sigma and the pi are equal. So guess what? The fields made by each of those two sections of mass across, quote, across from each other are the same size. So G1, well, is equal and opposite to G2. So the net G at that location from those two contributing sections of mass is 0. And guess what? There are however many other oppositely oriented across the shell from each other sections of mass that also contribute to the net field of that location. But the short story is the net field inside a shell is 0. Yeah, I'm still here. I'm just letting that sink in. Okay, so but there is a field inside the shell, but it's not from the stuff outside of the location where something is, because there's still a bunch of mass inside this. You know, if we took this actually hollowed out shell, the field inside is 0. But what we're trying to show here is, you know, what if we're here? What if we're here at a radius r, where here's, you know, let's call this Earth. This is Earth's radius, capital R. So how strong is the field at little r? Well, the field, again, from all this stuff, which can be made of an infinite number of super thin shells, the field inside each of those shells is 0. So from all this stuff out here, net field is 0. So the field really goes like this: G M enclosed over R enclosed squared. And that's maybe, this would be better written as a G as a function of R. All right, so how much mass is enclosed when we're at R? Well, let's see. Mass enclosed, mass enclosed, mass enclosed depends on volume enclosed. We can define a three-dimensional volumetric density that's mass per unit volume. All right, and that can be equal to, well, mass of the Earth over volume of the Earth, or it can be equal to mass enclosed, that's not a dot, over volume enclosed, if density is assumed to be constant, which it isn't, but who cares? It's more fun if we think it is. So mass enclosed, look, we can say that mass enclosed is V enclosed over V Earth times M Earth. Right? I just took this and solved for mass enclosed. So we can say this is, let's see, G, oh wait, G over R enclosed squared. V enclosed, that's, I still dotted my N for some reason. V Earth mass Earth. I'm just going to shrinky dink this stuff real quick. Whoops. Okay, so let's see. Now, these volumes, right? Volumes. This is four, oh gosh. This is 4/4 pi r enclosed cubed, that's volume of a sphere, over 4/3 pi r Earth cubed, right? So these 4/3 pi's go, and we get that this volume ratio is the same as this ratio of cubes of r's. All right, so we get that mass enclosed is, yeah, sorry, I made a goofer back here, right? This is G, this is big G. This is my mass enclosed part. And here's my G over R squared part. Okay, so this is G as a function of R. So we can say that mass enclosed is mass of the Earth times R enclosed cubed over radius of Earth cubed. Right, that comes from here with that. So now we can say that G as a function of R is G over R enclosed squared, that's this part, times mass enclosed, that's this part, that's mass of the Earth times R enclosed cubed over radius of Earth cubed, and look, those two factors go with two factors, and we're left with G as a function of R is G M of the Earth over radius of Earth cubed times R enclosed. So the field strength is proportional, because look, this is numbers, those are numbers. Field strength is proportional to R. From distance, so there's R, distance from, that's really a vector. If we turn this into a vector equation, this says that G depends on magnitude of R, and it points inward. Inward, there's a R hat direction. Okay? So this is an expression for how strong Earth's gravitation, well, a theoretical constant density Earth, how strong that field is anywhere inside the Earth. It depends on how far from Earth's center you are. It's proportional to how far from Earth's center you are. So we can make a couple of graphs. Here's a thin shell of radius r. Well, we just said that anywhere, if we're doing g as a function of r, anywhere inside this shell, field is 0. And then we go boom. And then this, once we're outside here, the field is just like this thing were a point mass located at the center. And then this g out here, g out, is gm over r squared. Same thing, quite literally, same thing as saying g, this is like mass enclosed, and, well, r enclosed, I guess. That steps up all the way to, well, gm over big R squared, and then this drops off in an inverse square fashion. Okay, if we have a solid uniformly dense mass, well, remember, from here to here, what we get is a variance in g that is proportional to r. So we get linear up to here, where this is still g m over big R squared, and then this drops off in an inverse square fashion because g outside is still that. Those two inverse square drops are supposed to look the same. Okay, so this is an interesting result for us, right? Because again, we're talking about what if we're in this hole inside the Earth? Well, we have g that varies uniformly with r. Okay, so let's say we drill this big old hole through the Earth, and there's a place we could put an object in equilibrium, and that place happens to be right there at, and I'll just call it center. And that's because g equals 0. I should say this. I should really say g as a function of r is proportional to r. So g at r equals 0 is 0. And that means that mg equals 0. And that means that there is no force. And that's equilibrium. So if we displace this object from equilibrium, put it, say, there, we locate it at some distance r from the center, well, now there's a gravitational force towards the center because the field is towards the center. So now we can say via a net F, well, that mg is ma. Neat thing to note, right? This mass means, hey, mass is stuff that is affected by a gravitational field. This is gravitational mass. This says, well, mass is stuff that doesn't accelerate. That's called inertial mass. Inertial. Those are the two different aspects or different natures of mass. But guess what? Those things are numerically equivalent, even though they mean very different things. So this says that A is G, or that A is, now what did we say G was? Oh yeah, here's G. It's G mass Earth over R, okay, so it's G, big G, mass of the Earth, over radius of Earth cubed, R. That's it. Except for, right? When this thing is displaced this way, there's vector r. The force is in the opposite direction. So we throw a negative in here. And before, that's why we had this in the r hat direction. I'm going to drop that notation just for the sake of neatness. And so what happens is this thing, well, is going to have a position that changes as a function of time. All right, position is going to change because you release this object, it accelerates towards the center, it gets going, and then inertia keeps it going until it gets over here. But when it's over here, then there's a mg back towards the center, so this thing oscillates. And so because position varies as a function of time, so must acceleration. Oh, goodness. And there's a negative in there. And this is the same thing. Well, acceleration is the second the do this d yeah d nope sorry this is d squared r dt squared. Acceleration is the second derivative of position, is negative stuff times the position function. So here's a function. R must be some function where its own second derivative is proportional to itself with a negative in front. And that means there's only one function in the world that does that. RT must be, well, let's call it R max cos omega t. Could be a sign, but we're saying that we're going to say at time zero this thing is at some maximum displacement. And the rules of calculus say that if we take the second derivative, I am glossing over this, but you take the first derivative of this, and you get R max times negative sine omega t, but then times another omega, because you differentiate that dt, and you differentiate that again, you get negative. We got another omega out front. We're back to a cosine. Right? So this says that d squared r dt squared is negative omega squared. Well, what's all this stuff? It's this. And that looks like this. Don't it? It do. Which says that this object that we drop in there will oscillate with an angular frequency that is, well, I should include the negative, that is, well, that's that. This says that omega, this thing has an omega that's equal to radical g me over re cubed. Now, that we can use to say, well, omega is 2 pi over the period of oscillation, so the period is 2 pi divided by omega. Yep. So that's re cubed over gm Earth. And, well, I happen to know what the radius of Earth is. I'm going to write that up here. Radius of Earth. That's also not it. Radius of Earth. Why don't we go ahead and use 6.37 times 10 to the 6th meters. And mass of the Earth is 5.98 times 10 to the 24th kilograms. And we know what big G is, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So guess what? You do this, and you get, well, you're going to get an answer in seconds, but you divide that by 60, because there's 60 seconds in a minute, and you get 84 minutes. And here's what's nice to note. The period has nothing to do with little r. The period is constant, whether you drop something from a little tiny r or all the way out to the end at capital R. It doesn't matter. No matter what, this object that's dropped in there will oscillate with that as its period. That's pretty cool, right? This thing is a simple harmonic oscillator. This thing being the object that we drop in there is a simple harmonic oscillator. We know that. I know that. Some people know that because when we see this is a function whose second derivative is proportional to the function itself. The rules of really of calculus say that there's only one function in the universe that can handle that, and that is that if we define that function as a cosine or a sine, but in this case we'll call it a cosine. And cosine functions have some rate at which they repeat themselves. All right. And the calculus rules, when we walk through this, say, yeah, look, second derivative is proportional to r, or function itself. Just like we said, second derivative is proportional to function itself. Then we can analogize, right, this angular frequency here with these constants of proportionality here, and that's why we get this. And then we can use the definition of angular frequency, the rate at which full oscillations happen. And you plug and chug, and we happen to get this number. What say you? I say awesome. What about this? Let's say another object happens to orbit like it's VT. It's cruising right around the Earth, just above the Earth's surface. Let's neglect air resistance somehow. All right, well, we do a net F for that, and we get mg is mac. Gravitational, inertial, same thing. Well, numerically. G, well, we can write G, right? What's G? G is at the surface, right? G big M over Earth's radius squared is V squared over R, right? Right. Let's see, one factor of R can go. Well, V, right, here's G M E over R E. That's equal to V squared. Well, V is circumference over period, right? So that's 4 pi squared R squared over T squared, right? Okay, this is the radius of Earth. Let me do this a little differently. Watch this, because we're going to get into Kepler's third law there, and it's not quite where I want to go. So let's do this. Equals MAC, fine, and inertial, gravitational. So this is G, is V squared over R. Yeah, good. This is better. And we can still, now R here is our big R, radius of Earth. Now, let's say that still V is 2 pi R over T, right? So G is 4 pi squared R squared over T squared and over R again. So we get one of these to go with one of those. So that says that T squared is 4 pi squared radius of Earth over G. Or T is 2 pi RE over G. G at the surface, right? G at the surface this is RE. G at the surface is GM over R squared, big R squared. So that's 2 more factors of R squared in the top. And booyah, look at this. The period of that oscillation is 84 minutes. The period of this orbital motion is the same thing, right? So like orbiter passes right now and somebody drops something, and as orbiter gets here, thing goes hello, and the orbiter keeps going, and drop thing oscillates back, and orbiter gets here and the thing goes hello, and so the orbiter could hypothetically, of course, pass this object every time the orbiter gets to the top of the hole. Object is right there waiting for it. I mean, that's just awesome. If you don't think it's awesome, there's something fundamentally wrong with you. I mean, you don't have the same interest in physics as I do. Okay, so that, my friends, is a pretty deep dive into a neat set of physics phenomena. Okay, boy, oh boy. The important parts are the following. One, puns. Second, we can talk about net field inside something. In this case, gravitational field inside a shell happens to be zero. Happens to be, well, it doesn't happen to be. We can prove it physically and geometrically. Where are those thingies? There they are. There's an analogy for a different kind of field inside a different kind of shell. We'll get to that pretty soon. It's electricity. What else is important? Well, we can therefore talk about what is the field strength inside a solid object, and that is proportional to how far from that object center you are. And this is also, guess what, analogous to a different kind of field. It's electricity. Graphing is fun. And boom, we can use some Newton's second law analysis to identify a very special kind of relationship. Acceleration and position proportional, right? A proportional to r. Not r squared, not 1 over r, not the square root of r. And this might not be r, in some other cases might be x for position, okay, or height or something like that. Or theta, we might have angular acceleration and angular position for a pendulum. That says when you see acceleration, aka second derivative of position function, when you see that is proportional to position function, particularly with a negative out front, and a lot of the times, folks, what you have to be able to say is, I bet, I see acceleration, I see position, there's a constant. I bet I can physically justify why there's a negative in there. In this case, we can because we displace this way, acceleration is this way. This is a restoring acceleration or a restoring force. Restoring means try to get back to equilibrium. And that says, okay, I have to now either believe because you've told me or be able to justify that there's only one expression for position that can satisfy this relationship, and it must be that position oscillates. And it does so via a cosine function or a sine function. That's okay. Because the rules of calculus say when we differentiate this function twice, we get negative omega squared times the position function. Right? And then we can say, look, negative omega squared times the position function is the acceleration, or look, negative stuff times the position is the acceleration. Therefore, these things are, well, equal. And that defines for us the angular frequency of this specific oscillator, where angular frequency is the rate at which full oscillations happen, right? The rate at which full oscillations happen. Therefore, we can define, in this case, the period of oscillation happens to be 84 minutes. And this was just a pretty cool thing that we get those periods of, well, oscillation, because circular motion is oscillation, all right? This object that happens to orbit just at Earth's surface has the same exact orbital period as this thing's oscillatory period. Holy cow. I am going to have some more water and less coffee. So, I leave you in bliss and satisfaction at a problem well solved. Okay? All right. Farewell.